Hello everyone. Our project is the electronic controlled camera lens for the Ranger test station sponsored by Daktronics. Our team is comprised of mechanical engineers Kate Collars and me, Kate Madsen, joined by electrical engineering major Kaveen Jayamana.
The purpose of the Ranger test station at Daktronics is to analyze LED panels after manufacturing to determine that each individual LED functions as it should. This is done by inserting LED panels into the Ranger test station below the camera, which captures images of the panel lit up as red, blue, green, and white. The images are then run through Daktronics computer software, which is where any dysfunctional LEDs are detected.
Prior to running any test on LED panels, the focus, aperture, and camera height must all be adjusted in order to obtain a clear image that the software is capable of analyzing. Previously, all of these adjustments were done manually by an individual, and it was extremely time consuming. The purpose of this project was to design a system that would drastically reduce the adjustment time while being accurate and precise enough to achieve a clear image.
When designing the system, we had multiple specifications and constraints to take into consideration. For specifications, our design had to be capable of moving the aperture and focus rings on the lens within 1 degree of the desired location. Similarly, the z-axis had to be capable of moving within 1 inch of the desired location. Both of these actions also had to be done within less than 10 minutes total.
The constraints for this project included the system being safe to operate in a manufacturing facility. The system also had to be completely DC powered and duplicatable, as Daktronics has multiple Ranger test stations. Also, due to compatibility and ease of use, only certain motors and motor controllers were acceptable for this design.
The first step in our design process was coming up with a way to rotate the focus and aperture. Our solution was to use 2 custom-made adjustable ring gears around the lens that would mesh with a pinion gear attached to a motor that would be mounted on either side of the camera. The ring gears would be able to be tightened around the lens with a bolt on the outer edge of the gear. The next step was determining the amount of torque that would be needed from the motors in order to rotate the lens rings. The calculated torque required to rotate the lens rings was fairly minimal, as it was around 45 ounce inches. The weight of the arm holding the camera was then calculated next for the z-axis motor selection. With a little safety factor included in this calculation to ensure no issues with movement, the total weight was found to be 18 pounds.
After all calculations, we narrowed our choices for the focus and aperture motor down to a single one along with its controller. But due to unforeseen global circumstances, this motor and controller had to be disregarded. We then decided to use only SMC motors and controllers, although more expensive, because SMC parts were already used in the test station itself. 2 LER 30K rotary tables were chosen for the focus and aperture rotation. These motors are more than capable of handling the torque requirement of the lens, as they can produce over 900 ounce inches. They are also able to rotate to any point from 0 to 360 degrees with a repeatability of plus or minus 0.05 degrees. A LEFS 40B linear actuator with an enclosed lead screw was chosen for the z-axis motion. The maximum lifting load for this actuator is 45 pounds, which makes it very capable of lifting the required 18 pounds calculated.
With this design, custom parts were going to be necessary. 6 parts had to be manufactured, and these parts included the brackets used for mounting the rotary tables, the adapter shafts used to extend the pinion gears down to the ring gears, and the ring gears themselves. A slightly smaller gear was made for the focus and a larger gear for the aperture to avoid any collisions between the adapter shafts and the ring gears.
The whole system is controlled by Allen Bradley 1769 L18 ER Series BPLC, which was programmed using Studio 5000 ladder logic software. We use the program to monitor the torque of each actuator when moving. If any external force that would raise the torque is sensed, the whole system will be stopped. Both rotor tables always move in a counterclockwise direction to reduce any backlash effect. Therefore, if they have to move backwards, they'll have to travel beyond the target position in a clockwise direction and then approach the position in a counterclockwise direction. We also design an HMI to insert inputs and monitor the system status. Later, this interface will be integrated into Daktronics' proprietary software called Orion. The control unit is used to turn on and off the motors and reset the motor controllers. In the positioning unit, we can insert our desired position and also monitor the real-time actuator position information right next to it. Actuator status is represented by LED indicators panel. Also, alarm section informs user about any anomaly in the system. The alarms can be cleared by emergency reboot and reset buttons.
After combining all subsystems of the design, the full system functions as desired. Everything in the system is DC powered as requested by Daktronics. Combining the precision of the rotary tables with the ring and pinion gear system, the location of the lens is able to be within less than 0.5 of a degree of the desired position, which meets the specification of movement within 1 degree. The linear actuator for the z-axis is capable of moving wherever needed along the z-axis with a position repeatability of 0.02 millimeters. which is well within the required 1-inch location specification. It also has no issue lifting or holding the camera arm itself.
All three of the motions can be done in less than 2 minutes, which is well under the required 10-minute time. Safety has also been included in the system, which will stop all motion if any of the motors detect any external force, such as running into something. Although custom parts were required for this system, such as the ring gear, brackets, and adapter shafts, it is still relatively easy to duplicate for other Ranger test stations at Daktronics.
As we were not given a strict budget, it was not a major concern throughout the project. The goal was to keep the total of the project between $5,000 and $10,000, which is exactly where we ended up. All parts that had to be manufactured were done in IME Brookings, who Daktronics had already been working with on regular basis.
In conclusion, our system drastically reduced the adjustment time in between LED panels from the original time of an hour or two down to a couple of minutes. This will allow Daktronics to spend more time analyzing LED panels rather than adjusting them for the clear image.